Today we got a lot to do. Want to work on method and properties of least square estimates. Of course, so in the outline, I'm going to walk you through the method of least square estimate and the properties of least square estimate. You remember before now, um, we actually we got I think I walk you through method of estimating parameter. I remember I walk you through, uh, you know, using Rao-Blackwell theorem. The Rao-Blackwell theorem actually use a function of sufficient statistic that we derive by virtue of Fisher-Neyman factorization. And with that, we're able to obtain what I call minimal variance unbiased estimator. And in a situation where the sufficient statistic is complicated, we normally resort to using either method of moment or method of maximum likelihood. The method of maximum likelihood is based on sufficient statistic, and the method of moment is not based on sufficient statistic. Now, but when it comes to linear modeling that we started on Monday, okay, if you remember on Monday, I told you we're able to express the expectation of random variable in terms of parameters, okay? And the parameters in linear regression now need to be estimated. And what method are we going to use in estimating parameters in the regression model? And that very method is what we call the method of least square estimate, and I'm going to walk you through today. Now, I'm actually going to walk you through the theoretical development, using the first principle, what is the mathematics behind the scene of this particular method is actually going to be unraveled today. And I'm also going to walk you through the properties of least square estimate. Now, I need you to be focused right now. We want to start with the method of least squares. Okay. I remember on Monday, I actually introduced you to take a look at the simple linear regression situation whereby I actually want to relate the response variable to only one independent variable. Okay. And of course, in the specification of model, we actually going to specify what I call a stochastic model, a probabilistic model. Okay, a probabilistic model is a model that actually has an error component. If you take a look at this guy now, okay, the deterministic aspect is this guy, and this is the random aspect. The random aspect is what we call the error. And of course, I told you on Monday, assumptions assumptions in a model revolve around the error. Okay, so the error will enable us to investigate how valid is the model. I told you from the one, model is not the same as reality. Okay, the deterministic model will give us an exact representation of reality, but in a stochastic world, okay, in a stochastic world, we need a probabilistic model. And of course, in a probabilistic model, but on average, when I take the expectation of the response variable now, okay, taking the expectation of the response variable now, I'm actually going to have this guy. I'm going to have a beta naught plus beta 1s, taking the expectation of a random of a response variable y that indicates y varies. Y is a function of the error, it varies, and we're actually going to be seeking for the probability distribution of that. Now, I was able to get that guy equal to that guy because of the assumption that the expected value of error equal to 0. It is not as if error equal to 0, but on average, error equal to 0. And if I'm looking at it, for instance, if my X here represent the years of education, if I want to know, if I want to look at the effect of the years of education, okay, on income, okay, of course, if in my model I'm only considering years of education as a variable, there are other factors that could affect income that the model don't talk about. We're actually going to say on average, their effect is negligible. And that is what we mean by the expectation of the error equal to 0. Okay, now just like somebody asked in class on Monday about how do we interpret a beta naught and a beta one. When you take a look at a beta naught and a beta one, they are actually called regression parameters. We call them regression parameters. The beta naught is a regression constant. The one mathematician is going to call an intercept. And the beta one is actually slope. The two of them are regression parameters. They need to be estimated. If I really want to measure relationship between the response variable and the independent variable, the beta naught and the beta one need to be estimated. When they are estimated, they are actually going to have a curve. Okay, so we're going to say the beta naught curve is the estimate of beta naught, while the beta one curve is the estimate of beta one. Now, you remember the other time we said that the expected value of y equal to that in a situation where the beta naught curve is an estimate of beta naught and the beta one curve is an estimate of beta one, then I can also say this guy here is going to be an estimate of the expected value of y. Because we actually want to get the estimate of expected value of y. So the estimate of the expected value of y now is going to be beta naught cap plus beta one cap x. Okay, so which means the parameter that need to be estimated is actually beta naught cap and beta one cap. The beta naught and beta one that we call the beta one cap and that. Now, can you confirm again if you are still hearing me clearly? Is everyone still hearing me clearly? Okay, thank you so much. Thank you for confirming that. Now, if I want to estimate the beta naught curve and the beta one curve, of course, we can only estimate with sample information. So I'm actually going to collect a sample, right? I'm going to collect a sample of data, that is bivariate in nature, X1, Y1, maybe I'm going to, if I'm talking about n numbers of individuals, I'm actually going to be collecting two variables at a time, okay? Maybe one is, oh, what is your years of education? Okay, how many years of education do you have? And can you tell me your income? Okay, and that was why I got the first one there. You're going to see that. Okay, and the second one until the last one. And you know what we're going to do? If you remember what I told you the other time, okay, if I want to have a sense of a model that I'm actually going to fit, I need to generate a scatter plot. And what do we mean by a scatter plot? A scatter plot is just going to be a diagrammatical plotting of the response variable y against the independent variable s. And that is exactly what you are seeing now. Okay, now if you take a look at that now, then we're actually going to generate what I call the line of best fit. It is not going to be all the points that are going to be on the line. As you can see here, you got a point, they are all scattered away from the line of equal distribution. But you know what? We're actually going to draw the line in such a way that the point will be equidistant. And by the time we do that, we're actually going to call that the line of best fit. Now, if you want to go by what you did in high school, if you want to get this guy here, the beta naught, you're actually going to be looking at where that guy strike the y-axis, okay, which is going to be the values of y when s equal to 0, Okay, and of course, if you want to go by the method you use in the high school, if you want to get the beta 1 curve, which is going to be the slope, you can draw a triangular, can draw something on the line, then you're actually going to, but that is, figuring out the beta naught and beta 1, the estimate of that using graphical approach. And let me also tell you this, there's always going to be, if you make a prediction with a model, I'm actually going to call that y cap. The original y is actual value of y. For instance, if I are given a particular years of education and I was able to have a prediction for income, and I now look at the distance between the actual income in the data, okay, actual income in the data and the predicted income, of course, I'm actually expecting a difference because I do not expect my model to actually give out exact reality. There's always going to be a distance between what your model predicts and what happened in reality, which is what we're going to call the error. That is going to be the error. Error is going to be a gap. And what are we looking for? We're actually looking for a situation where we can minimize that, where we can minimize the distance. Okay, that's what we're looking for. Okay, now we actually want to estimate, we need a formula now for beta naught, because if you want to get a value, if you want to get an estimate, okay, you actually need an estimator. Estimator is a formula. Okay, what formula am I going to use if I want to get the estimate of beta naught? What formula am I going to use if I want to get estimate of beta 1? Okay, and let me tell you this, if you want to get the formula, you're actually going to ensure the formula that will lead to drastic reduction in the error. I'm going to say that again. When you are seeking to get an estimator for beta naught and beta 1, you're actually going to take into consideration, the approach that minimize the sum of squared error. I'm going to use this opportunity to tell you that, um, you know, this is the situation. We believe that around the response variable y, there is a total variation. Okay, around the response variable y, we got 100% variation. Now, and the variation around that can be broken down into two. Okay, it's going to be broken down into two, the variation that can be explained and the one that cannot be explained. I'm going to say that again. The total variation around the response variable y, can be broken down into what I'm going to call explained variation and unexplained variation. Explained variation is a variation, you know, explained by the model. The variation explained by the independent variable in the model. The unexplained variation is the one that we can attribute to error. And what we want to do is we always want to minimize the unexplained variation. If we want to minimize the if we're able to minimize the unexplained variation, then the beta naught and the beta 1 that we got, we're actually going to be great. So therefore, we are looking for an approach that will minimize the sum of squared error, which we call the total unexplained variation. Okay, and if you're seeking for that, you need to first understand, when I make a prediction with my model, which is going to be y cap, then the error is going to be the distance between the actual response and the predicted. Okay, and don't forget, if I have 20 number of observation, I'm actually going to have 20 errors. Some of the errors, they're going to be negative. Some of the errors are going to be positive. But you know what we need to do is to square them. Why are we squaring them? We want to square them. For this time, if I get a -2 and 2, when I square -2, when I square this guy, it's going to be 4. When I square 2, it's also going to be 4. Okay. Now, when we square that, okay, that's going to become error squared, right? And we know why we're squaring that. We're squaring that because we're trying to tell the world -2 and 2 has the same effect, okay, in terms of the distance to the to the line of equal distribution. Now, and now I'm going to sum them. Okay, this guy here is what we call the sum of square error. Another name for the sum of square error is what we call unexplained variation. Unexplained variation. And don't forget, the unexplained variation is what other variables explain, the variable you did not consider in your model. We want a situation whereby the effect of the variables you did not consider in the model to actually be minimal. Okay, now I needed to take a look at this guy now. I'm actually going to plug in. What is my y cap? This is my y cap. I'm actually plugging the y cap here now. Okay, now you can see the sum of square error that I call unexplained variation now is a function of the estimator, beta naught cap and the beta 1 cap. And you know what? The moment we got something like this in mathematics, if I want to minimize, I'm actually going to use what I call the principle of optimization. And what is the principle of optimization is actually to differentiate. I'm actually going to get the derivative. Okay, I need the derivative of this with the respect to beta naught. I need the derivative of this with the respect to beta 1. Now that's going to take me to the next. Take a look at what I'm doing here now. So what am I doing now? I'm trying to differentiate the sum of square error with the respect to beta 1. And after doing that, I'm going to get this. I'm going to simplify, and I'm going to set that to 0. Okay, when I set that to 0, what am I looking for? I'm actually going to solve for beta 1. Okay, all of this, I needed to walk through all of that. What I'm trying to do is just to solve for beta 1. And in the end, I got a formula for beta 1. This is the estimator for beta 1. Can you give me 1 second? Just 1 second. Okay, now when you simplify all this guy now, the formula, the estimator for beta 1 cap now is going to be this guy. Okay, and another way to write that is this. What of in a situation where the examiner has to derive this, the beta 1 cap is actually what you're seeing right now. Is there anyone who need clarification on this? Is there anyone? If you really understand how to navigate this, if you really understand how to go about this guy now, I need you to say yes, or you give me a thumbs up if you understand that. But if you need clarification, you need to be able to ask me question. If you need clarification, ask question now. Okay, thank you so much for confirming that. So what I did is to differentiate the sum of square with the respect to beta 1. We equate that to 0. And of course, we solve for beta 1. And at the end of the day, this is what we have. Now, after doing that, the next thing we want to do now. So the next thing we want to do now is how do we now get the beta naught? Okay, we differentiated the sum of square error with the respect to beta 1. Okay, and we proceeded this way. You're going to do the same to the beta naught. You're going to differentiate with the respect the sum of square error with the respect to beta naught, equate it to 0, and in the end, you're actually going to see you're going to have your beta naught cap to be equal to that. Your beta naught cap is going to be a function of the beta 1 cap. So the estimate, so this guy, the expression that we have now we actually call them least square estimate. Why do we call them least square estimate? Because we call them least square estimate because we believe the estimate that we got here, we have put into consideration minimizing the sum of square error, and that was why we actually go by way of optimization in mathematics. Now, when you take a look at this guy now, okay, we also call that SXY that we call the covariance, and this can also be called XSX. Okay, I needed to take a look at all of that. Okay, so that is the least squared estimate. And don't forget, when you take a look at this guy now, the XSS, like I said, is certain as days. That, that is a deviation around A. So take a look at that. Okay, now since we now have the formula, okay, we got an estimator now for beta 1 cap, for beta 0 cap. Now we can now apply this on data set. Okay, we take a look at this data set right now. Okay, take a look at this data set. Okay, you're actually gonna see here. I'll give you. Can you see confirm if you're seeing what I'm sharing right now? Okay, thank you so much. Thank you for confirming that. Okay, now I need you to take a look at the table here. Okay, use the method of least square to fit a straight line to n equal to 5 data point given, you're giving s, you're giving y. Okay, and of course, if this is x and y, you need to get xy, you need to get x squared, and this is going to be the sum of s, the sum of y, the sum of xy, the sum of s squared. Now you're actually going to go back to the formula now. Okay, you go back to the formula. Okay, the formula here. Okay, you need sum of xy. Okay, the sum of xy. Okay, you've already gotten that. The sum of xy is actually 7. Okay, you're going to plug that in. So you're plugging each of these in into the formula you've created, and at the end of the day, we've gotten our beta cap 1 to be 0.7 and the beta null cap to be that. So the beta null cap, don't forget the formula here. Okay, the mean of y. The mean of y is just going to be the sum of y, the sum of y here divided by 5. This is going to be 1, right? And that was why you are actually having that. So 5/5. So now you got a beta 1 cap to be 0.7. You got a beta 0 cap to be 1. Okay, so the 0.7 and 1 now become the least square estimate. Okay, is there any question about this before moving forward? Is there any question? Okay, now if there's no question, I'm going to move to the next slide. Now, in the next slide, we want to talk about the properties of LSA simple linear regression. You remember the other time when we were talking about properties of estimator, right? In the properties of estimator, we actually have the unbiasedness property. You remember we talk about the efficiency, we talk about consistency, we talk about sufficiency. And right now, we also want to investigate, okay, how unique is our parameters here. The beta naught, the estimator for that, the beta naught cap and the beta 1 cap. We want to investigate that. So, and that was why we said the properties of least square estimator. Okay, and when we investigate that, we actually going to investigate for the unbiasedness property. We want to see whether they are unbiased or not. Not only that, we're also going to have a way to derive the variance of estimator. Why do I need to derive the variance? You remember the other time when we were investigating for either efficiency or consistency, we actually need an expression for the variance of an estimator. So we're also going to derive the variance of the estimator here for the beta naught cap and the beta 1 cap, because when we derive the variance for them, we're actually going to use them in statistical inference. We're going to use them to construct confidence interval. We're also going to use them to test hypothesis. Okay, now when you take a look at this, I need you to recall, give me 1 second. This is not changing. I think I'm gonna reshare again. It's like that is not changing. Give me 1 second. I'm gonna reshare that with you really quick. Okay, so like I said, I want to talk about the properties of least square estimate, and recall about the step in regression when I started on Monday. We said we want to design a parametric model, right? We want to design a parametric model, a function, right? Then after specifying, an appropriate function, like what we do in statistics, we four of us specify our model, right? And after specifying our model, the next thing is to fit the model to data. Okay, we feed the model to data, and we are able to obtain the value of theta by minimizing a cost function. A cost function is the sum of square error I talked about the other time. We want to minimize that. And the theta here is the beta naught and the beta 1. The beta naught and the beta 1. Okay. And number 3 is, how do we quantify how accurate our estimate for theta is? For instance, we got 0.7 here and 1 here. How are we so sure that the result that we got here are optimal? Okay, and the only way to tell is to investigate the property of a least square estimate. Okay, now I want to revisit simple linear regression again. Okay, this is the specification of the simple linear regression. Why it's expressed like that. And of course, assumption is that error E1 up to En are independent random variable. And of course, the expected value of the error should be 0. And the variance of the error should be sigma squared. The variance of the error, this is talking about constant variance. Another name for constant variance is what we call homoscedasticity. Homoscedasticity. So we expect that the variance of the error should be sigma squared. I told you the other time, the reason why model is not the same as reality is because there's always going to be a gap between model and reality, and there's going to be error, right? Now, the assumptions on the model revolve around the error time, and one assumption now is that the expected value of the error should be 0. The variance of the error should be sigma squared. The error is any factor that could affect the response variable, but our model, we don't capture that at the moment. And since we don't capture that at the moment, we actually place an assumption on them that they are on average, their effect is negligible. And that was why we said the expected value of error equal to 0. And we also assume that the variance of error, the dispersion around the error should just be sigma square, should be constant. And of course, we've been able to derive an estimator for beta naught and beta 1 by, trying to perform a derivative on the sum of square error, with an intention to minimize that. Okay, so you actually differentiated with respect to beta naught, you set to 0, you solve for beta naught, you differentiate with respect to beta 1, you set that to 0, you solve for beta 1, and we now arrive at an estimator. Okay, the beta 1 cap now, they are estimators. Okay, they are estimators. Okay, we actually call them estimators. Okay, we call them estimators, and whatever value we obtain from them will be estimates. So because of that, this guy here is an estimate. These are estimate. Okay. But this guy here, we call them estimator. You remember that? Estimator. This guy here is an estimator. Okay. Don't forget, estimator is a formula. Okay. Or method that we use in estimation, and whatever that is assumed by the estimator is actually going to be called estimate. Okay. Now take a look at all of that. Now the next thing we want to do now, we now want to investigate the property of an estimator. And how can we investigate? You know, if we want to investigate the property of an estimator, we're actually going to test for the unbiasedness. Let me tell you this. In this class, if I give you assignment, maybe I want you to work on relationship between income, relationship between income and years of education. And I ask you to go into American population. And maybe I give you an assignment to randomly select 50 individuals. You collect data on their income and you collect data on the years of education. I want to believe if you use a formula, here, okay, every one of you will get different results. Even if you are working on the same thing, you choose the same sample size. When your beta 1 cap and your beta 0 cap will be different from others. I'm going to say that again. If 1,000 investigators should go into population, they work on the same thing, they choose the same sample size, and maybe probably they are working on the relationship between income and years of education. I want to believe because they are choosing individuals at random, they're actually going to get different results for beta 1 cap and the beta 0 cap. And because of that, if I have 1,000 individuals, I'm actually going to have 1,000 values for beta 1 cap. I'm also going to have 1,000 values for beta 0 cap. In that situation, you remember the same thing that I mentioned when we were talking about estimator. Estimator becomes a random variable because it varies. And because of that, we may want to investigate the distribution. Okay, we want to investigate the distribution by plotting the histogram. And if the distribution is normal, and the only way the distribution can be normal is to go by way of central limit theorem, the central limit theorem that guarantee you taking a sufficiently large sample. Okay, the central limit theorem that guarantee you taking a sufficiently large sample. Okay, when you take a sufficiently large sample, we expect the distribution of the statistic or the distribution of the estimator to be normal. Now, we can now find to show in that situation when that happens, then it means the expected value of a beta 0 curve will be beta 0. Don't forget, the beta 0 is a parameter. The beta 0 curve is an estimator. Okay, so situation where this is going to happen, it means the central limit theorem has taken its course. So the expected, so we want to prove to the world that the beta 0 cap and the beta 1 cap are unbiased. Okay, so when they are unbiased, of course, we expect, you remember the expectation of an estimate of theta cap should be equal to theta. You know, in this case, we got two form of theta, the beta 0 and the beta 1. Can you still hear me? Is everyone still hearing me? Okay, thank you so much. Thank you for confirming that. And we also want to show for the variances, because when you have an estimator, how will you investigate for efficiency? How will you know whether the estimator is consistent? Of course, we need the variance. And as you can see, the variance of beta 0 is derived to be this. The variance of beta 1 cap is derived to be that, and the covariance is derived to be that. Now, when you pay attention to the variance of beta 0 and the variance of beta 1 now, you're actually going to see that they are actually going to be consistent, because you can see the sample size in their denominator. When you see a sample size in the denominator, of course, that is to show that they're actually going to be consistent. But what we want to do now is just to walk you through how these are derived. Don't forget, this course is theory of statistics. How do we come about this? That's going to be the next point of call. I'm actually going to show you how an estimate of beta 0 cap and beta 1 cap is unbiased. And I'm also going to show you how we derive the variance to be all of these. Okay, we need this property need to be satisfied before we can move forward in statistical inference. Okay, before we can move forward in statistical inference, it becomes a matter of urgency to actually look into this. Okay, now I need you to pay attention now. We want to start the proof right now, and this is going to be more mathematical. And all what I need from you is to pay attention now. Okay, we want to derive, we want to go algebraic right now. You actually need the knowledge of algebra here. Okay, now we need to first note that the sum of square for deviation is 0. Okay, you need to take note of that. And not only that, this guy can also be expressed as that. We are using that. If that guy is expressed as that, then the same thing also with this. Okay, take note. Because we're going to start with assumption. So what do we want to do now? We actually want to show that beta 1 cap is an unbiased estimator. So if you want to do that, I want to find what is the expectation of the beta 1 cap. Then we're going to go back. What was the beta 1 cap? Okay, this is the beta 1 cap, right? We want to take the expectation of both sides. And don't forget, okay, that's what we want to do, right? We want to take, and don't forget this guy here. Okay, that guy is XXX. You remember? That denominator is SSS. Okay, now that is how, take a look at this guy now. You see that the beta 1 cap is defined as that. We're taking expectation of both sides. Now we take expectation of both sides. Remember that this guy is the same thing as this guy from here. You see that? That guy is the same as that guy. Okay. Now, I want to find the expectation of that. We're going to have an assumption now. Assumption is going to be expectation. We only grab the random variable y. X is fixed. X is fixed. But y is random. So expectation right here is going to grab y because y is random. Expectation is going to grab something that is random, something that varies. It only makes sense to find the average of something that varies. When something do not vary, we don't need the average. Okay. Now that's how we find ourselves here now. Expectation grab the random variable y. And from the beginning, if y equal to beta 0 plus beta 1 x plus the error, the expectation of y is actually what? Beta 0 plus beta 1 x. Don't forget, we have an assumption that the expected value of error equal to 0. So because of that, I'm actually going to be substituting this guy now for expected value of y. That's what I'm doing right now. Expected value of y equal to beta 0 plus beta 1 x. Then after that, what I'm going to do is just to simplify, and I actually need to expand, where I'm going to say beta 0 multiply that guy and beta 1x multiply that guy. When I do that, I'm actually going to find myself here. Okay, I just use this guy to multiply x minus x bar. Okay, and after doing that, oh my God, take a look at this guy. Under the assumption, the sum of square deviation equal to 0, and that is how I got the 0 here. Okay, and if you take a look at this guy here, is the same as that, right? It's the same. Now, if I want to rewrite now, so this guy is going to be 0. I'm only going to have this guy and 1 over that, and I move to the next slide. I'm actually going to have this guy. Oh my God, take a look at that. Do you know that this guy here, okay, is the same thing as SSS? And if you take a look at what I have now, the SSS and the SSS, they're going to cancel out. And what do I got? I got a beta 1. That is a proof that the expected value of a beta 1 cap is actually going to be equal to beta 1. And we're just trying to show the world right now that beta 1 cap is an estimator. Beta 1 cap is an estimator. Does that make sense? Okay, is there any question? Is there any question? I need someone to confirm again if you are still hearing me clearly. Is everyone still hearing me clearly? Okay, thank you so much. Now I just show you how the beta 1 cap is an estimate or is an unbiased estimator. We're also going to investigate the unbiasedness of a beta 1 cap. Now, to remember the other time, I'm going to take you back to the beta 1 cap. Take a look at this guy. Okay, all what we're going to do is to introduce expectation to both sides. Okay, introducing expectation to both sides. That's exactly what we're doing here. Okay, we introduce expectation to both sides. Now the expectation is going to multiply out. So I'm going to have expectation of y bar. I'm going to have this. And don't forget, x is a constant, mean x bar is also a constant. If x, independent variable is a constant, it's fixed. In regression analysis, independent variable is fixed. The dependent variable that we call the response variable is random. So anything fixed is actually going to be a constant. And that is the reason why you see this guy coming out of the expectation. Okay. And the beta 1 cap is a variable. I told you the other time, if 1,000 investigators should go into population working on the same thing, they figure out their beta 1 cap, they're actually going to get different value. And that is why it's a random variable. Then it's going to be under expectation. Okay. Now, when you take a look at this guy, we're going to do something, if you take a look at this guy now, when I introduce 1 over n and summation, we cancel n. Summation from I1 to n is still n, but I need it. Okay. Now, but you take a look at this guy, don't forget the model, expected value of y is beta naught plus beta naught plus beta 1s. Okay, now what I'm going to do now is to use this guy now to multiply each of that. When I use 1 over n summation times beta naught, is still going to be beta naught because beta naught is a constant. Then when I use this guy to multiply x, that's going to be summation x over n. That's going to be x bar, okay, which is this guy x bar here. And don't forget, this guy is here. Oh my God. This guy cancel that guy now. And of course, I'm actually going to have beta naught. And this is how we prove that the expectation of beta naught cap is actually going to be equal to beta naught. Take a look at that. Take a look at the proof right now. And this is how we're able to show to the world that the least square estimator, they are unbiased estimator. So they are unbiased estimator because the expectation of that gave population parameter. Okay. I think the next is deriving the variance. But you know what? I'm not going to rush you on the variance. I'm going to leave this to the next class. So in my next class, I'm actually going to start my derivation from how do we derive the variance of beta naught? How do we show that the variance of beta beta naught is going to be that? How do we show that the variance of beta 1 is going to be that? And how do we show that the covariance is going to be that? Okay, I think I'm actually going to walk you through that in the next class. Okay, is there anyone who want to ask question or who need clarification before I go today? Is there anyone?
Hi, Professor.
Yeah, go ahead.
I actually have no question for this class, but just a little like technical question on our midterm two. It's like I have finished the exam only like 30 seconds before it comes to an end. So I actually have two pictures that failed to upload, but I tried to email you right after I finished the exam. I'm not sure if the email has been like delivered quite well or uh
Okay, so you run out of time and you are not able to you now submit through the email, right?
it's like I have like 30 seconds left to upload those pictures, so I failed to upload them. But I like send you an email right after I finish the exam.
Oh, okay. So if you send me an email after you finish the exam, of course I'm taking that into consideration. I'm in the process of grading, and I
Mhm.
think I'm also been grading those ones sent to me by email. Okay,
Okay, thank you
so
so
let's not worry.
much.
You're welcome.
Okay, thank you.
You're welcome. Okay, is there any other question? Okay, in the absence of question, I want to thank everyone for attending my lecture today. And of course, I'm actually going to return to in-person teaching on Monday. And I'm going to say, enjoying your Thanksgiving celebration. I wish you successful Thanksgiving celebration, and make sure you all stay safe. I think somebody said I was wondering about completing. Let me just say the chat that came in. Oh, okay. I think I would like to speak with the person. Um, okay, I'm gonna do this. Give me 1 second. Okay, like I said once again, make sure you all stay safe and have a wonderful, very successful Thanksgiving celebration. Bye for now, everyone. See you on Monday in person.